It's another flipped classroom lesson, and this one is on diffraction. Now you might want to grab worksheet number 3. You'll need it in a few minutes. I'll let you know when. So first, let's talk about what diffraction is. If I make some waves in the computer simulator, there we go. You can see these waves were coming down. They're very colorful. The greens are crests, the troughs are red, and you are looking from the top down on these waves. Now I've placed an obstacle right here. Let's see what happens when the waves run into it. Here it goes. So a lot of things you can see at once. The waves are reflecting off of the surface here, kind of what we'd expect, and the waves over here are going around it. But look what's happening right here. Instead of going in a perfectly straight line, some of the waves are just bending a little bit inwards into this dark spot right here. That's weird. Are we seeing that right? Now this is a pretty high frequency wave. Let's turn down the frequency. That'll increase the wavelength. You can see bigger wavelengths here, and let's see what happens. Whoa, look at all this bending around the corner. The waves do not go in a perfectly straight line down. They will bend around corners. That bending around corners has a name. It is called diffraction, which is the title of this video and the subject we'll be discussing. For my next example, I have a single slit, and this example is now going to be on your worksheet. It's number 1. There is a single little slit right here, so the waves are going to come down from the top of the screen. These two big bears are going to block everything except for what gets through this little tiny opening. Let's see what happens. Do the waves go straight through and cast a sharp shadow? No, they don't. They seem to come out in a little bit of a cone. You can see there's also this dead region right here. But for the most part, it's coming out in an ever-widening cone. And I can draw that like this right here in 1A. I just drew a little cone coming out right there. Now let's see what happens if we make the wavelength a lot bigger. What do you have to do to the frequency to make the wavelength bigger? You have to lower it. So let's lower the source frequency and see what happens. Let's lower it way down. And now you can see the waves that are coming out are spreading out in a much wider cone. In fact, it's pretty close to a semicircle itself. So I would draw a much wider cone like this one right here. All right, now let's try a larger opening, like in number 3 on your packet. So I now have a much larger opening, and now I'm going to start it with a pretty high frequency wave. It's going to be a small wavelength. Let's see what happens. This is actually closer to what we'd expect in the particle model. The waves look like they're just going straight through, at least at first. There's this big bulk of just straight through, although you can see some very interesting things happening on the sides. There is a little bit of spreading out. For the most part, it's straight through, with a little tiny bit of spreading. Let's now try a lower frequency, long wavelength waves and see what happens. These are spreading out a lot more. So we, generally speaking, get much more diffraction with a longer wavelength or / lower frequency. So let's see what happens when we put an obstacle in. This corresponds to number 6 on your sheet. I have to use a box on this simulator instead of a circle, but the results will be pretty much the same. We're going to first throw a nice high frequency wave on here. That'll be a very short wavelength. Let's see what happens. Here comes our wave. It hits the box. And I don't see a whole lot of diffraction here, maybe a little tiny bit. So in this case, we get a pretty sharp shadow, just like we did in the shadow lab. Light must have a pretty high frequency short wavelength, so it casts sharp shadows when you shine it on obstacles. And that seems to be what we're getting here. Now let's lower the frequency, up the wavelength a little bit here, and see what changes we get. Do you see any more diffraction? I do. Down here, it looks like they're coming back together again. So more diffraction, once again, same pattern. Let's lower the frequency even more. Big wavelengths. At this point, by the time the waves get to the bottom of the screen, they've basically just gone around the obstacle. You can see there's a little gap right here where there aren't many waves, but by here, it's as if the obstacle weren't even there. The waves have just so bent around it. This can help you fill out number 6 on your sheet. The bigger the wavelength, the more stronger bending, more stronger diffraction we get. So now we're going to do the last one on the sheet. What happens when waves go through 2 slits at once? So I have 2 of them right up here. Let's let her rip at a pretty high frequency. Now you can see we're getting patterns of waves, no waves, waves, no waves, waves, no waves. This is interesting. If you look at the bottom of your screen, the waves hit here, then there's no waves, waves, no waves. If this were light, and we know that light is a wave, we would get a bright area here, dark, bright, dark, an alternating pattern, and a pattern that's much wider than our slits. Does this look familiar? I hope so. This is what we did in the lab when we shot a laser through a couple of little very narrow apertures. We got a pattern that looked just like this. And the spreading out has to do with diffraction, but it doesn't quite explain why we have these areas where there's no waves. So we'll look into that in the future. But you can just copy this down for number 8, the first one, with the short wavelength. If we want to make the wavelength longer, we lower the frequency, so I will do that, and we're going to see how the pattern changes. Note the distance between these bands of waves. There you go, lower frequency. And I think you can see that the distance between these two has increased. So the longer wavelength, the more these bands of light spread out, which kind of makes sense. The lower the wavelength, you get more diffraction, so things spread out more. Now, at this point, you should have filled out all the graphics on your handout. You'll have to go back and answer all those written questions afterwards. And to sum up, diffraction is when waves bend around obstacles. If you force waves to go through a little hole, the smaller that hole is, the more bending you're going to get. And the longer the wavelength, the more bending you're going to get. All right, and that's all.